So Adams' method refers to a family of numerical techniques used for solving ordinary differential equations. These methods are based on interpolation of previously computed values of the solution to estimate future values. There are different variations such as the Adams-Bashforth method or the explicit method and Adams-Moulton method or implicit method. Each of it utilizing a set of past data points to approximate the solution at the next step. These methods are commonly used for efficiency in solving stiff and non-stiff ODEs. In scientific and engineering applications.
Adams' method. Adams' method is a numerical technique used to solve ordinary differential equations, particularly initial value problems. It is classified as a linear multi-step method, meaning it calculates the future values using multiple previous points rather than just the most recent one. This makes it more efficient compared to single-step methods like Euler's and Brauncotta. There are two types of Adams' method. So the first one is the Adams-Bashforth method or explicit, a predictor method that estimates the next value based on previously computed function values. It is computationally faster but may suffer from stability issues. The second one is the Adams-Moulton method, implicit, a corrector method that refines the predicted value by incorporating both past and future function evaluations, offering greater stability at the cost of additional computation.
Definition of terms: ordinary differential equations that describe the relationship between a function and its derivatives. They use the model system that change over time such as physical processes. Initial value problem where the solution to avoid is solved given initial condition as a specific starting point, usually specified as a value for the function and its derivative. Linear multi-step method, a family of numerical methods for solving problems that use multiple previous ones instead of just the most recent. This is to calculate the next value to improve efficiency and accuracy. Adams-Bashforth method, a method in Adams family that uses previous point to predict the next value of the solution in a straightforward, explicit method. It is faster but may not be as stable as the using method. Adams-Moulton method. This method is that it corrects the predicted value using a combination of past and future points, providing greater stability at the cost of additional computational effort. Polynomial interpolation, a technique used to approximate functions by creating a polynomial that passes through known data points. The Adams method is used to approximate the solution to the by creating polynomials from previous value interpolations. The interpolator method, a two-step approach to numerical methods where one step predicts the solution and the answer is based on value condition. Adams-Bashforth is predicted and Adams-Moulton is correct. Lastly, step 7. The difference in the input variable between successive points in a numerical solution. Larger step size reduces computation time and may introduce errors, while smaller step increases accuracy but requires more.
Adams' method used for apportionment involves calculating a modified divisor and then dividing each state's population by that divisor, rounding up to the nearest whole number to determine the number of seats each state receives. The key step is alternatively adjusting the divisor until the total number of allocated seats matches the required total number of seats, favoring smaller states by always rounding up. Now, steps in Adams' method. Number 1. Calculate the standard divisor. Divide the total population by the total number of seats to be allocated. Second, choose a modified divisor. Select a divisor slightly larger than the standard divisor. Third, calculate the modified quota. Divide each state's population by the chosen modified divisor. Fourth, round up. Round each modified quota up to the nearest whole number. This is the upper quota. Fifth, check total seats, add up all the rounded upper quotas. Sixth, adjust divisor if necessary. If the sum of upper quotas is exactly the total number of seats, you are done. If the sum is too large, choose a larger modified divisor and repeat steps 3 to 6. If the sum is too small, choose a smaller modified divisor and repeat steps 3 to 6.
Next, we're tackling the sample problem of apportionment. We'll be using Adams' method to figure out how to fairly distribute seats in a representative body. Think of it like this. we have a group of people who need to be represented, but different areas they live in have different population sizes. Apportionment helps us make sure each person gets equal representation no matter where they live. To understand how Adams' method works, let's imagine a scenario. Picture a country with 5 states. We'll call them A, B, C, D, and E. Now, each state has a different population. State A is the smallest with only 53 people. State B has a few more people with a population of 201. State C is a larger population of 808. And State D is even bigger with 917 people. Finally, State E is the most populated with 1,993 people. We have 25 seats available in a governing body, like a Congress that needs to be divided between these 5 states. The goal is to allocate the seats as fairly as possible, based on the population of each state. This is where Adams' method comes in. It's a mathematical process that helps us ensure larger states get more seats while still making sure smaller states have a voice. My teammate will walk you through the exact steps involved in Adams' method and show you how we arrive at the final apportionment of seats.
So this is a solution in solving Adams' method. So first thing we do is find the standard divisor. So we have an example of, suppose a nation has 5 seats with the population shown below and a representative body with 25 seats. How many seats should each state get? So we have state A, the total population of 53, state B, 201, state C, 808, state D, 917, and state E, which is 1,993. And add all the population, so we got the answer of 3,972. And of course, to get the standard divisor, we need to divide the population by 25. So 3,972 divided by 25 is 158.88. So to get the standard quota, we need to divide 53 by 158.88, which is the standard divisor. So 58 divided by 53 divided by 158.88 is equals to 0.336. And 201 divided by 158.88 is equals to 1.2651, and so on. And the total for the standard quota is 25. And to get the upper quota, just round off. So 0.336 becomes 1, 1.2651 becomes 2, 5.0856 becomes 6, 5.7717 becomes 6, 12.5441 becomes 13, and a total of 28. And that is too big, so I'm gonna adjust the divisor. The divisor was 158.88. We're going to adjust it up, make it bigger, so we get smaller upper quota. So I'm gonna do this a few times. There's no formula in finding modified divisor, and that works, so we have to do guess and check. So I tried 158.88, and that gave me 28 seats, which was too big. So that means I need to increase my divisor. So for example, I used 200, but I didn't put the computation and the solution of 200 since it gives me an upper quota of 23, which was too low. So I have to decrease the divisor in order to get a larger result. So I need something in between 158.88 and 200. To save time, I have found out that 183 is a good thing to guess. So dividing the 53 divided by 188 is equal to 0.2896. So 201 divided by 183 is equals to 1.0984. 808 divided by 183 is equals to 4.4153. 917 divided by 183 is equals to 5.0109. And 1993 divided by 183 is equals to 10.8907. And just like what we did in the upper quota, we need to round off. So 0.2896 becomes 1, 1.0984 becomes 2, 4.4153 becomes 5, and 5.0109 becomes 6, and 10.8907 becomes 11. So add all the upper quota and we get the number, and we get the total of 25. And that is our final apportion, which means that 183 is our standard divisor that we need. So, and it is just right. So our final apportion is 1, 2, 5, 6, 11. And that's how we solve Adams' method.
Hello everyone! Today I will explain how we arrive at the final apportionment for each state based on the given table. So for state A, the population of state A is 53. We divide this by 158.88, which gives us a standard quota of 0.236. Since we need whole numbers, we round it up to 1 for the upper quota. Next, we divide 53 by 183, which gives a modified quota of 0.2896. Since rounding must ensure fairness in apportionment, state A gets 1 representative in the final apportionment. Next is state B. State B has a population of 201. Dividing by 158.88 gives a standard quota of 1.2651. Rounding up the upper quota is 2. Using the modified divisor, 201 divided by 183 gives a modified quota of 1.0984. Since this still falls close to necessary allocation, State B receives 2 representatives. State C. The population of State C is 808. Dividing by 158.88 gives a standard quota of 5.0856. The upper quota is 6. Using the modified divisor, 808 divided by 183 gives a modified quota of 4.4153. Since the final apportionment must sub 25, State C gets 5 representatives. State D. The population State D is 917. Dividing by 158.88 gives a standard quota of 5.7717. Rounding up, the upper quota is 6. With the modified divisor, 917 divided by 183 gives a modified quota of 5.0109. This aligns with fair distribution, so State D receives 6 representatives. And lastly, State E. The largest population belongs to State E, which has 1,993 people. Dividing by 158.88 gives a standard quota of 12.5441. The upper quota is 3, and again using the modified divisor, 1,993 divided by 183 gives a modified quota of 10.8907. To keep the total fair at 35, State E receives 11 representatives. And that gives us a total population of 3,972. Where the standard quota is 25, upper quota is 28, and the modified upper quota as 25. After applying the apportionment method, we adjust the distribution to ensure fairness, keeping the total representatives as 25. The final apportionment for each state is for State A is 1, State B is 2, State C is 5, State D is 6, and lastly, State E is 11. And that's how we determine the final answer for each state.
Adams' method is a numerical technique for solving ordinary differential equations, using multiple previous points to improve accuracy. It comes in 2 main forms, the Adams-Bashforth and the Adams-Moulton. This method is efficient because it achieves high accuracy with fewer function evaluations per step, making it useful for non-stiff problems. However, it can be sensitive to initial conditions and may struggle with stiff equations after requiring a predictor-corrector approach to enhance stability. Despite these limitations, Adams' method is a powerful tool for approximating solutions to ODEs efficiently.